Hello everybody. In this video we continue discussing optimization problems, and this is the lecture where we will go through example 5. So we have this function here, 2x squared plus y squared, that's defined on R2, so any ordered pair x, y. Okay, and we would like to compute the maximum and minimum values of this function over this bounded region. Okay, and the bounded region that's defined by this inequality, so x squared plus y squared less than or equal to 16, that's just the disk that's centered at the origin of radius 4. So everything inside the disk and also on the boundaries. Okay, so that's my R. All right, and now we're going to follow the steps that we've discussed in our previous example, but our analysis of the function on the boundaries will be slightly different. Okay, so the first step is the same. We set up the system where we compute the partials, set them equal to 0, and find all critical points. So in this case, it's once again just one point, the origin, 0, 0. We check if that point belongs to the interior, and it does. So we're going to consider it for the extreme values. Now we can also say right away that 0, 0 is where the absolute minimum happens, and we can do that analytically, because if you look at the function, it is 2x squared plus y squared. So no matter which values of x and y we plug in, we always going to get positive, right? If x and y are positive. If both x and y are 0, then we get 0, and that is the smallest value that this function can take. Okay, so just analytically we can state that's where the absolute minimum happens. All right, so we know how to do this part. Now, how do we proceed for the boundary portion of the solution? Well, I'm going to take a look at the curve. And now in this case, I have one curve. It's a closed curve, right? And I have an equation of it, or rather inequality. But for the equation part, this would be, if I just look at the boundaries, that would be x squared plus y squared is equal to 16, right? If I'm only interested in the boundaries, not on the interior. Okay, well, there is another way to represent this object. And we've learned that at during the very first week of the class, and that is by looking at the parametric description of a circle, right? So we know that if we have the center and the radius, we can rewrite our curve in terms of parameter t. So here you see I'm writing x is equal to 4 cosine t, y is equal to 4 sine t, and my t is bounded between 0 and 2 pi. So if that is my parameterization, then I can also use that to rewrite my function now in terms of t. Okay, so I'm rewriting my function and saying, instead of looking at the function in terms of x and y, let's rewrite it in terms of t. Okay, and what I'm doing, I'm plugging in this for x and this for y. Okay, so remember what our function was. Okay, let me go ahead and remind you. Our function was 2x squared plus y squared. So I'm substituting 4 cosine t for x, 4 sine t for y. Okay, now once I do that, we get the following expression. 32 cosine squared t plus 16 sine square of t. And I'm going to split up 32 cosine t into a sum of 16 cosine t and 16 cosine t. And why is that? It's because I'd like to isolate it like this and say this is 16 cosine squared t plus 16 square sine t. Sorry, not 16 square, 16 sine square of t, right? And that, of course, is just 16. That is the Pythagorean identity that we use in trig, okay? So that gives me this function of t just in terms of one of the trig identities, right? So we have 16 cosine square of t plus 16. All right. Now we can analyze what happens to this function. We know that cosine is bounded. Okay, the cosine function for any value of t, it is between -1 and 1. And if we squared, right, because that's what we have over here, we have cosine squared, then now it's bounded between 0 and 1, and that gives us an easy way to determine what the maximum and minimum values of our f of t is. Okay, so what are they? Well, if the largest value of cosine square of t is 1, then that will give us 16 times 1 plus 16. Then the maximum value would be 32. Now, when does that happen? That happens when cosine of t is either negative or positive 1. And we know that cosine takes those values at t is equal to 0. Okay, that's where cosine is equal to 1. And t is equal to pi. That's where cosine is equal to -1. Okay, so again, how do I do this? If this is the maximum value for cosine squared, then if I plug that 1 back into the equation, I get 32, and it happens for 0 and pi. Okay, now what about the minimum value? Well, if cosine is equal to 0, then we just get 16 times 0 plus 16, and that gives us 16. Okay, when does that happen? That happens when cosine is equal to 0, and cosine is 0 at these two values of t. Okay, so now we can list our points, and here they are. Okay, we have 0, 0, that's from the first step, and then you just evaluate our substitution, right? So back substitution. Okay, if t is equal to 0, what are the points? Okay, then the point is 4, 0. If t is equal to pi, that's -4, 0. And then for pi over 2, we get 0, 4. And for 3 pi over 2, we get 0, -4. Okay, but what happens here? We know that the maximum value will happen for t is equal to 0 and pi, so that's the points 4, 0, -4, 0, and then the minimum value is 0, and that happens at the origin. Okay, so the other points are not points where absolute values happen, right? Those are local extrema. Okay, so if you go back over here, we can mark it. Let me go ahead and mark it with purple. Okay, over here, this is where we get absolute minimum. Okay, at the origin, and then at these 2 points, so 4, 0 and -4, 0, we get absolute maximum. Okay, all right, so let's quickly review what we've done here. First step is the same. We compute our partials, set them equal to 0, find the critical points, check if these points are on the interior of R. Once that's done, we'll look at the curve. And in this case, this is a perfect example where parametrization is very useful because it is one of those curves that we know how to write parametric equations for. And once we convert our function to a function of just one variable with values very well known, right? It is easy to analyze and see where we have maximum, where we have minimum. Okay, so that is it for this particular problem. So we have one more problem to discuss for computing absolute max and min of functions of two variables on a bounded region. Okay, thank you for watching.